Welcome to The Explainer. We're about to pull back the curtain on a part of your network you probably never think about, but it's the hero that makes all your local connections even possible.
So think about it. You plug in an Ethernet cable, you connect to Wi-Fi, but have you ever really thought about what's going on between your computer and your router? I mean, it's not some neat, tidy conversation. It's actually kind of chaotic. And figuring out who or what manages that chaos is the key to, well, understanding how a huge chunk of modern networking really works.
Okay, so before we can really appreciate the solution, we have to talk about the problem. And the problem, the villain of this story, is basically just noise. When you're just sending raw ones and zeros through the air or down a copper cable, that signal is super easy to mess up. I mean, look at this. On the left, that's the dream, right? A perfectly clean, orderly stream of data. But the reality? That's what you see on the right. It's a jumbled mess. You've got electrical interference, signals getting weak over distance. All sorts of things can flip a 1 to a 0 or a 0 to a 1. And when that happens, your important file just turns into digital nonsense. So yeah, someone's got to step in and clean up this mess.
And that's where our hero comes in. This meticulous organizer that tames all that chaos, well, it's time to give it its proper name. The data link layer.
Now, you'll hear tech folks call this layer 2 of the networking stack. Its whole job, its entire reason for existing, is to manage the conversation between two devices that are right next to each other on the network. We're talking your laptop to your router, your phone to your Bluetooth speaker. It doesn't care about where your data is going on the internet. Its only concern is getting it to that very next stop, that directly adjacent node, safely.
So its mission, if you will, is super clear. Take that messy, unreliable physical signal we just saw and turn it into a clean, dependable, error-free link. It's like the ultimate traffic cop for your local network, making sure every single piece of data gets handled correctly.
So how does it pull this off? It's not magic, though it kind of feels like it. It has this really powerful and honestly pretty clever toolkit. And it all boils down to 3 key functions that work in perfect harmony.
And here they are: framing, flow control, and error control. 1 to package the data, 1 control the speed, and 1 to make sure it's all correct. Let's break them down.
Okay, first up, framing. You know, this is kind of like putting a letter in a very specific envelope. The data link layer grabs the data from the layer above it and wraps it up, putting a header on the front and a trailer on the back. This whole package is called a frame, and that frame makes it super clear to the receiver, hey, this is the start of the message, and okay, this is the end. It creates these nice, neat, manageable chunks.
Then you've got flow control. This is so important. Imagine you're talking to someone, and you're talking a mile a minute, but they're a slow note taker. They're going to get completely overwhelmed, right? They'll miss stuff. Flow control is basically the listener being able to say, whoa, slow down a sec, let me catch up. It's a feedback mechanism that stops a fast sender from just drowning a slower receiver in data.
And the last piece of the puzzle is error control. This is maybe the coolest part. How does the receiver know if the data arrived intact? Well, it uses some clever math to create a kind of digital fingerprint for the data, often called a checksum. When the data arrives, the receiver calculates its own fingerprint and compares it to the one that was sent. If they don't match, bingo. It knows the data got corrupted somewhere along the way.
A really simple way to see this in action is with something called a parity bit. You just add 1 extra bit to a string of data to make sure the total number of ones is, say, always an even number. If just one of those bits gets flipped from a 1 to a 0 during transmission, suddenly the count is odd. The receiver sees that, knows something went wrong, and can say, hey, send that one again.
But, you know, just being able to spot an error isn't the whole story. Especially with today's super fast networks. We need to handle this stuff efficiently. And that's why, over the years, the protocols that manage this whole process have gotten a lot smarter, faster, and stronger. So in the early days, we had something called stop and wait. And it's exactly what it sounds like. You send one frame, then you stop, and you wait for the other end to send back an acknowledgement, or ACK, saying, yep, got it. Only then can you send the next one. It works for sure, but man, is it slow. That's why we now use pipelining. This is more like a conveyor belt or a pipeline, just constantly filled with frames. You can send a whole bunch of them before you even need to hear back.
And this chart, wow, This just shows you how huge the difference is. On a 1 gigabit link, that old stop and wait method uses a pathetic, 0.027% of the link's capacity. It's basically wasting everything. But look what happens when you just pipeline 3 frames at once. The utilization jumps to 0.08%. That's almost a 300% improvement just like that. This isn't a nice to have, it's absolutely essential for the kind of speeds we're all used to. And even pipelining has its own flavors. There's a strategy called go back in. It's pretty straightforward. If, say, frame number 5 gets lost, the sender has to go back and resend everything from that point on. Frame 5, frame 6, frame 7, all of them. But then there's the smarter, more modern approach, selective reject. Here, the receiver can be more specific. It can say, hey, I got 6 and 7 just fine, but I missed number 5. Can you just send me that one again? It's a little more complex to implement, but it's way more efficient.
Okay, I know. We've been getting pretty deep in the weeds here with frames and ACKs and pipelining, but why does any of this technical stuff actually matter to you? Because this unsung hero, this data link layer, is working for you right now. It's the reason your Wi-Fi connection to your router is stable and doesn't just drop out constantly. It's why when you plug your computer into a wired network, your data gets there without being corrupted. That Bluetooth connection between your phone and your headphones? Yep, that's it too. Literally any reliable point-to-point data transfer relies on this.
So it all comes back to that number, 2, as in layer 2. The data link layer is the invisible workhorse that does the dirty job of taking the messy, chaotic physical world and turning it into the clean, reliable stream of data that everything else, the entire internet, is built on top of.
I mean, without it, data wouldn't even get from your computer to your router reliably, never mind across the world. Which, it really makes you think, doesn't it? What other invisible systems, what other unsung heroes are working right now, just behind the scenes, to power our entire digital life? And, well, that's what we're here for, to explain them.